Hello, participants. It's my joy to welcome every one of us again to another section of this training on time series forecasting using R. Uh, we still have a few things to learn before we move to forecasting. One thing that is very, very essential anytime we are making predictions or forecasting is stationarity. So we are going to look at stationarity tests. Um, Stationarity test. So what is stationarity? A stationary time series is a time series where there are no changes in the underlying system. There is no trend, that is, uh, the trend is constant. There is no heteroscedasticity, that is, you have a constant variance. The structure of autocorrelation also is constant. Then there is no seasonality or any form of periodic components. Concerning assumption one, this is what we are talking about. We can see that this is mean reverting, a sort of constant trend. This is approximately a kind of situation where we have constant variance. And here we have two plots, one showing the presence of autocorrelation, that is correlation between the measurements at two different points, where the time interval between the values is called lag. So generally, autocorrelation results in patterns. So for instance, if you look at the first one, we can see a rising trend in the pattern. But when time series without autocorrelation, then it exhibits some kind of randomness. The stationary time series has a constant autocorrelation structure over the entire series. Why is stationarity very important? It's important because without stationarity, most time series models will break down. Because in making our prediction and forecasting, it's based on the assumption that there is independence between different points. And one of the best way to understand this is to understand the stationarity of the time series. So it's important that we identify non-stationary time series. And to do that, we normally start with the sequence plots. Sometimes we look at the summary statistics or check our histogram. But usually we perform some statistical tests, usually based on OLS regression. We have the augmented Dike-Fuller, Philip-Heron, and we have our KPSS. We are going to look at these different approaches. With respect to sequence plot, this is simply the plot of the time series. It's always the first step in any time series to see the underlying structure. And this is the essence of trying to decompose our time series so that we check for trend, we check for seasonality and randomness, just as we have done. Then for summary statistics, we can compute the mean and the standard deviation of the chunks. Large deviation actually means non-stationarity. We can plot the histogram Approximately normal distribution usually indicates stationarity. Um, in case we have non-stationary time series, one way to uh, make it stationary is through differencing. And if in a bivariate model, both variables are different stationary, then one way around the problem is to run the model with different variables instead of using the variables at levels. But this option may not be acceptable because when you obtain your variables in difference form, it may not be in accordance with any of the economic theory. Another major issue is that the model may be omitting some important long-run information because difference variables are usually thought of as representing the short run. And again, we may not have the correct functional form any longer. Um, so one of the most important tests for stationarity is the use of Dickey-Fuller test or augmented Dickey-Fuller test. The test is based on a random walk and the fact that a random walk has a unit root. So if the variable in question follows a random walk, it is therefore not stationary. And this is why when testing to determine if a variable is stationary, it is said to be testing for a unit root. So this is a typical case of the Dickey-Fuller test. So the test is based on this regression. So our interest is the this coefficient, the value of this coefficient. We test whether it is equal to 0 or not. That is the essence. So the test assumes that the error term follows Gauss-Markov assumptions. The test statistic does not follow the t distribution, so the critical values have been produced specifically for the test. So a constant and thread could also be included in the test. So the test statistic will still be the test for whether the coefficient on the lagged variable, that is the beta, is equals to 0. So in this case, the test is for a unit root against no unit root. That is our HO. Our HO in this case is test for non-stationarity because that is what we either reject or not reject. There is a little bit of difference between Dickey-Fuller and augmented. And the keyword is augmented because Dickey-Fuller was actually augmented to obtain augmented Dickey-Fuller test. The error term in Dickey-Fuller test usually has autocorrelation, which needs to be removed if the result is to be valid. And one way to do that is to add lagged dependent variables until the autocorrelation has been mopped up. So the carrying out of the test, everything is as the same as Dickey-Fuller. So this is the basic difference we can see here. So, and we try to determine the number of lag-dependent variable to be included using whichever information criteria of choice. That we use Akaike, Bayesian, Swartz, or whichever. So when a variable contains two unit root, it is said to be I2. If it's 1, then it is I1. And needs to be different. If it's 2, then it needs to be different twice to induce stationarity. When using the ADF test, the data is first tested to determine if it contains a unit root. If at level it doesn't contain unit root, though, standard is fine. So we say it's I0. If it is not I0, then it could be I1 or I2 or of higher order of unit roots. So in this case, the ADF test needs to be conducted on the difference variable to determine the level at which it becomes stationary. It's very rare to find I3 or IR that we don't even go near. Most economists time series actually are I1. So most tests using Dikey-Fuller and augmented Dikey-Fuller techniques are considered to have low power because the power depends on the time span of the data rather than the number of observations. So if the coefficient is roughly equal to 1, but not exactly, the ADF test may indicate a non-stationary process. And because of this little use with Dikey-Fuller, uh, it gives rise to the use of various other ones. And if you want details of that, there are quite a lot of very useful time series econometry textbook that can explain uh, uh, the details. So instead of using augmented Dikey-Fuller, we may resort to Philip Perron and other methods. And to carry out the stationarity test in R, very straightforward. We need this package, unit root cointegration URCA. And the function for the ADF is UR.df. So this is our climate data time series. Type, for the type, we have three types. We have trend, if it's trend is stationary. Then we have drifts, in case you just want to work with the constants. Then we have none, in case you don't want to include the constant and the trend. But usually the best thing is start with the trend, check it, then introduce the constant. If it's constant, you type drift here, then none. Then it's always good to select your last, to automate maximum lag selection, optimum lag selection. So in this case, I use my AIC. So if I've done it, this is what we obtained. Now, by way of interpretation, this value here and this value are the important ones that you have to consider. This is the critical value. So the moment you look at this critical value, usually I normally advise students look at it in absolute terms. But since this is actually less than this, then definitely it is stationary, and this is at levels. But if it's not stationary at levels, then you have to take the first difference. If you want to take the first difference, it becomes so simple to do. Say DI, type DI. Anyway, I think I will illustrate it when we get to R. I think my system button is not functioning well here. Okay, for Philip Perron. For Philip Perron, there is a little bit of little difference in terms of the syntax to use. This our data. Then you have two types. You have the Z tau and the Z alpha. Then the model is either trend drift or none. Then, but the lags is divided into short and long. So you run it again. The way you interpret is the same, or the way ADF is interpreted. Then the last one is Kwiatkowski, Philip, Schmitzen, KPSS. This is a bit different because in this you reverse the way the hypothesis is stated. Because in this case, the null hypothesis is test for stationarity. Unlike the other ones is test for non-stationarity as the null. So we have to take notes. And that is why most of the time we normally recommend that you use one of those ones or the two, but make sure you use this one because you are reversing it. So, but you have to compare, then the interpretation now is different. All right. So this is about the stationarity test. Next, we are going to see how to operationalize this in our studio.